So we're going to talk about a few cautions about graphics. This will be an extension of other things that we've already learned in this chapter. So as we have seen, graphics can offer clear and meaningful summaries of statistical data. However, even well-made graphics can be misleading if we are not careful in interpreting them. And poorly made graphics are almost always misleading. Moreover, some people use graphics in deliberately misleading ways. In this section, we will discuss a few of the more common ways in which graphics can lead us astray. So, perceptual distortions. Many graphics are drawn in a way that distorts perception of them. The figure below shows one of the most common types of distortion. The dollar-shaped bars are used to show the declining value of the dollar over time. The problem is that the values are represented by the lengths of the dollar bills. A 2015 dollar was worth 35 cents in 1980 dollars and therefore is drawn so that it is 35% as long as the 1980 dollar. However, our eyes tend to focus on the areas of the dollar bills. So they're drawing the length as 35%, but we're not looking at 35%. If we kind of match that up, that would be about right here, and we'd see this much of the dollar, but instead they shrunk the whole thing. They're looking at the areas, what we see. And the area of the 2015 dollar is about 12% of the area of the 1980 dollar, because both the length and the width are reduced by 35% of those 1980 sizes. So really, instead of looking at 35% of it, we are looking at 12% of that big picture. So this gives the perception of the value of the dollar shrink even more than it really did. The lengths of the dollars are proportional to their spending power, but our eyes are drawn to the areas which decline more than the lengths. You got to watch the scales as well. Both graphs show the percentage of college students since 1910 who were women. Both graphs show the same data, but they look very different because their vertical scales have different ranges. At first glance, the first graph appears that the percentage grew by a huge margin after about 1950. But the vertical axis scale does not begin at 0 and does not end at 100%. So this scale only goes from 30 to 60. The increase is still substantial, but looks far less dramatic if we redraw the graph with a vertical axis covering the full range from 0 to 100%. That's one of the very common things that they will do, is to just not set it at 0. From a mathematical point of view, leaving out the 0 point on a scale is perfectly honest and can make it easier to see small scale trends in data. Nevertheless, as this example shows, it can be visually deceptive if you don't study the scale carefully. Some of the issues with another issue would be that that can arise when graphs use nonlinear scales. That is, scales in which each increment does not always represent the same value and change. The graph shows how the speeds of the fastest computers have increased with time. At first glance, it appears that speeds have been increasing almost linearly, because linearly it looks like a line here. That's what that means. And it almost looks like it's a line. It might look as if the speed increased by about the same amount from 1990 to 2000, from here to here, as it did from 1970 to 1980, because it's basically in a line. However, if you look more closely, you'll see that each tick mark on the vertical scale represents a tenfold increase in speed. So it doesn't go from 0 to 10, and then 10 to 20, and then 20 to 30, and 30 to 40. It's going from 0 to 10, 10 to 100, to 1,000, to 10,000, to 100,000. So it's going up at a exponential growth there of 10-fold. So now we see that in terms of millions of calculations per second, computer speed grew from about 10 in 1970 to 1980. So it went from like 10, 1980, we'd hit at about 1,000. So it's gone from 10 to 1,000 And from about 10,000 to 2,000, and in 2000, we're at 1,000,000. So that's huge, from 10,000 to 1,000,000 versus from 10 to 1,000. This type of scale is called an exponential scale or logarithmic scale because it grows by powers. In this case, powers of 10 and powers are exponents. For example, 3 is the exponent in 10 to the third equals 1,000. More issues with these graphs. It is always possible to invert an exponential scale back to a linear scale, as shown in the second graph. However, comparing the two graphs should make clear why the exponential scale is so useful in this case. The exponential scale clearly shows the rapid gains in computer speeds, while the linear scale makes it impossible to see any detail in the early years shown on the graph because they all look like they're at about 0. Because it jumps from 0 to 20,000 and then goes jumping up to close to 100,000. More generally, exponential scales are useful whenever data vary over a large range of values. Percentage change graphs is college getting more or less expensive. If you didn't look too carefully, the graph might lead you to conclude that after peaking in the mid-2000s, the cost of public colleges has since fallen. But look more closely and you'll see that the vertical axis on this graph represents the percentage change in cost. The drop-off therefore means only that cost rose by smaller amounts, not that they fell. Actual college costs make it clear that they rose every year. So here's the actual college costs with a bar graph, and you can see in both cases, with public or private, that it's increasing. But over here, it looks like it's gone way down. Graphs that show percentage change are very common. You'll find them in the financial news almost every day. But as you can see, they can be very misleading if you don't realize that they are showing change rather than actual values. And here's our change in college costs and our actual college costs in dollars. So pictographs are graphs embellished with additional artwork. The artwork may make the graph more appealing, but it can also distract or mislead. Below is a pictograph showing the rise in world population from 1804 to 2040. The numbers for future years are based on United Nations intermediate case projections. The lengths of the bars correctly correspond to world population for the years listed. However, the artistic embellishments of this graph are deceptive in several ways. For example, your eye may be drawn to the figures of people lining the globe. Because the line of people rises from the left of the pictograph to the center and then falls, it might give the impression that the future world population will decline. In fact, the line of people is purely decorative and carries no information. The pictures add visual impact, but can also be misleading. Notice that the horizontal scale time is not linear. So if you notice here, it's not going in increments that are exactly the same. We jump from 1804 to 1927. That's 123 years. And then we go to 47 years to get up to 1960, and then only 14 years to 74, then 13, and then 12, and then 13, and 12, and then 16. Notice that horizontal scale time is not linear, and the more serious problem with the pictograph is that it makes it appear that the world population has been rising linearly. Because of the amount of years they chose, it looks like this is a linear growth line that's happening right there, and it's not. However, the time intervals on the horizontal axis are not the same in each case. As I was saying, for example, the interval between the bars for 1 billion and 2 billion was 123 years, but that interval between 5 and 6 billion is only 12. In other words, the bars were spaced equally for visual effect, but the spacing does not convey accurate time information. Pictographs are very common, but as this example shows, you have to study them carefully to extract the essential information without being distracted by the cosmetic effect.